Okay, I am posting this because if I'm late getting back from our field trip to the cadaver lab, I want to make sure that we have something that you can kind of start working on. First thing I want you to do, check over your practice problems. I left 166 through 167 out of the binder, those 2 pages on limiting reagent and limiting reactants. And I want you to check those over. I'm going to try to post a PDF of the key so you can check those over. The other thing that you should do, I left some review questions out of the end of the chapter 12, and I'd like you to turn those in. We'll go over those on Tuesday if I'm not back, and answer any questions about those. So what I'd like to do today is show you how to calculate percent yield. And well, to explain why you might need to do this and what's going on with this. But first, I'd like to kind of show you this practice problem. And this is out of page 162. And I'm going to assign 162 through 163 in the binder. And so this is the first question off page 162. And you've got this reaction. And this is magnesium. And we're reacting with nitric acid. And we're yielding magnesium nitrate and hydrogen gas. First thing we need to do is get it balanced. It's not balanced. We have 1 magnesium here, 1 there. I have 2 nitrates here and 2 hydrogens, so I believe all I need to do to balance that is that. And it then asks what type of reaction this is. Guessing most of you already figured this out. And it's a single displacement reaction. We're displacing hydrogen with magnesium, okay, and we're yielding hydrogen gas as a result of that. So the first part of this question is asking you to calculate how much hydrogen you might yield off of this. And the first thing you need to recognize is that one of these reagents is limited. And it tells you which one that is. It says we have 40 grams, 40 points, so 2 significant figures there, 40 grams of the magnesium, and we have excess nitric acid. So this is in excess, which means this is limiting, and this is going to determine how much of the products I can yield. So we're going to run this through a stoichiometric calculation to determine how much of the hydrogen we might yield. So we need to convert this to moles of magnesium. And molar mass on the periodic table that I had, I came up with this. You might have something a little different if it has more significant figures on your periodic tables. Oops, got that G, excuse me. Cross off that one. We then need to convert to hydrogen. We need to run it through, use the ratios in the stoichiometric coefficients to determine how much hydrogen. And it's a 1-to-1 ratio in this case. So 1 mole of hydrogen produced for every mole of magnesium consumed. I am going to write that. I know mathematically that adds nothing to your calculation, but I'd like to see that there, and I'd like you to have that there. Just make sure that you know you've converted now. You're working with hydrogen, not magnesium, so this is canceling. And then we need to convert that back to grams. Okay, so 1 mole of hydrogen is equivalent, and keep in mind this is hydrogen gas, is H2. So on the periodic table, this is the one I had, it was 1.008, but we've got 2 atoms of hydrogen in every molecule, so we have to double that. That's 2.016 grams of hydrogen. So now we converted to grams of hydrogen, and if we calculate that out, assuming I did my math right, I came up with 3.3 grams, 2 significant figures here, so I've got 2 significant figures in my answer of hydrogen. Okay, so in the next question, or the next part of the question, number 3, it says, if 1.70 grams of hydrogen is produced, what is the percent yield of hydrogen in this case? So when we actually run the equation, theoretically you should be able to yield this amount. This is number 2, by the way, this is number 1. So we should be able to yield that amount theoretically, but we didn't. And why might that be the case? Well, there are a couple of reasons for that. I'm going to switch over to there. One reason might be temperature. might be too cold to completely react the products. Remember that these are in motion. These molecules are in motion according to collision theory of matter. They need to collide with one another. Collision theory of chemical reactions. They need to collide with one another with enough energy and in the right orientation to actually react. And if they don't have enough temperature, they might not do that. Concentration might be significant. If there aren't enough of these in solution, they may never really run into each other. They might just be bouncing around in water molecules and never really contact one another. The purity of the reagents, there might be impurities in one of these reagents. Perhaps this one, since this is a pure metal, that might prevent them from reacting with one another. Pressure, if it's gases, pressure can be a limiting, can limit your reactions. And lastly, what solvent is used? Are you using water, alcohol, or benzene, or something else that could limit your chemical reactions? So for whatever reason, we didn't yield as much as we calculated that we might yield. We only yielded 1.70 grams of this. So to calculate the percent yield, we're just going to take our actual, so the actual yield, we're going to divide by the theoretical. That's the maximum we could possibly yield, theoretical yield, okay, which is what you calculated here. So this is your theoretical yield. And of course, multiply by that by 100 and we'll come up with a percent. So my actual yield was 1.70. My percent, or my theoretical yield, was 3.3 grams. So multiply that by 100. And I come up with a yield of only about 51%. Okay, two significant figures here, so my percent is reported to two figures there. Okay, so hopefully that makes some sense. Like I said, I hope I'll be back by the time you get to this so we can talk about this together as a class. But if not, that should give you enough to work with. Number 4, I think on page 162 is almost exactly the same. And then on page 163, you'll have to write an equation for that reaction and balance it. And then the rest of the reaction, the rest of the questions kind of deal with that reaction. So good luck with that. And again, I hope I'm back by the time you get to it. All right. And